Okay, in this video we're going to take a look at another property, the final mechanical property, and that is the angular momentum. Just like we did with the previous one, it's very helpful to think about what are the units and what are the equations for linear momentum or linear impulse. Of course, linear momentum is just simply the mass times the velocity. It has units of kilograms because that's the units for mass, and the units for velocity are meters per second. So a kilogram meter per second. Angular momentum, you're going to see, does not have the same units. I know for energy, it did. Energy, it did have the same units. But if you just think about for rotational motion, you know, we're focused on torque, not force. With angular momentum, it is actually given the same name. It doesn't have the word momentum in it, but it does have different units. So the symbol for it is L. I've done a little bit of research for why the letter L was chosen. Some people say it's because of the right-hand rule. It has to do with the fact that this is a cross product and the fact that the moment of inertia and the motion of the angular velocity are at right angles to each other. Some people, there's several different reasons why. Regardless of whatever the reason why it is capital L is the symbol for angular momentum, lowercase p is the symbol for linear momentum, and then we just got to translate these properties. So the equivalent property for mass in the rotational world is I, and the equivalent property for linear velocity is angular velocity, which is I omega. Now that's going to produce units of kilogram meters squared, because that's the units for I, and then divided by S, because the units for this guy are inverse seconds. So when I multiply it, that gives me 1 unit of S on the bottom. Those two are not equivalent to each other. So it is a different physical property. It is still considered the momentum, but the angular momentum, but does have different units, unlike angular energy, which still has units of joules. All units are exactly the same. So that's just the definition of angular momentum. Let's take a look at the linear impulse. Linear impulse can be seen through the second law. This really is not the best explanation of the second law. Just to remind you, the formula for acceleration is delta v over delta t. We could even put a delta m on there also. We could allow the mass to change. M times delta v, if I do delta v divided by delta t, that's a. If I do m times delta v, then I get delta p divided by delta t. Important to understand. We can then take this equation to expand it to get f delta t equals m delta v. This guy is called impulse, and this guy is called the change in momentum. Okay, so now let's make the translation. Let's translate this into angular motion. So we would not talk about force, we would talk about torque. What causes the torque? Well, it's I times alpha, as we've already pointed out. Let's expand that in the same way that we did here. So that would be I times delta omega over delta t. If I take I times delta omega, I times the change in the angular speed would be the change in the angular momentum. That would be delta L over delta t. But we can do the same thing we did over on this side by taking the delta t over to this side. And what we would get is angular impulse and on this side we would get the change in angular momentum. Okay, so two properties, angular momentum and angular impulse, both of which can be used in exactly the same way as we would have used the linear properties, but just being applied to rotational motion. So let's just take a quick look at how that would work out. Let's start with the simplest possible example that we can. Let's say we have a metal disc, which we've been using for all of our example problems, and we want to calculate what is the angular momentum of a spinning disc. So this may be driving a belt or something like that. Who knows what the thing is being used for? But the formula is L is equal to I omega. Okay, but now in this case, I do need to come up with what is the correct formula for this particular geometric shape. And we've been using this one before. So it is 1/2 mr squared times omega. So therefore L would be equal to 1/2 5.89 times 0.34 squared, that's the radius of the disk, and then multiplied by the angular speed, which is in the correct units. Be careful, remember, a lot of times you may be given rotational motion in terms of revolutions per minute, and that needs to be translated into radians per second. So in this case, it's already done for us. 42 to get an L of 14.367, and that would be kilogram meters squared per second. If we finished it by reducing down the number of sig figs, we would end up with 14.4 kilogram meters squared per second. Okay, and we can use this number because we're going to be able to then take it down here and translate that by using the formula that we just used up here. And that is that torque is equal to delta L. So torque is equal to the change in L over the change in T. And we already have all the numbers, so there's no reason to redo all the calculations. In the end, if I want to bring this entire thing to the stop, so I'm going to put my fingers along the edge until the thing slows down to a stop. And if it takes me 2.8 seconds, then I should be able to figure out how much frictional force did I apply to that disk. So we're going to take it to 0 angular momentum, starting with a total angular momentum of 14.4. We're going to do that in 2.8 seconds. So as a result, we'd find that we'd have a torque of 5.13 Newton meters. Now that's not the final answer because, again, we're not looking for the torque. What I want is the force. So in this case, that would lead to a force, which is the torque divided by the lever arm. In that case, that is 5.13 divided by 0.34 to give me a frictional force of 15.1 newtons.